Swayam Prabha. Digital India. Educated India.
In this lecture, we continue to discuss about how to connect our theoretical exposure with the computational activities in aerodynamic flows. So, this was the place where we ended our last lecture. We pick up from the point where we left, and let us look at this figure, where schematically we are trying to explain that there is a uniform velocity which is impinging on an airfoil at an angle of attack, and you have a boundary layer formation, a viscous dominated region which also moves into the wake of the airfoil. There is a very thin separation, and by and large you can say that you have a low angle of attack, primarily attached flow on the airfoil surface, and beyond the dotted region you have a practically inviscid flow. But remember that this flow has a mix of viscous and inviscid regions, and we remember that this flow field that we saw from a computational result was such a flow field. Of course, here it appears that the alpha is 0 degree. Now, there could be questions coming to your mind that what if we try to solve this problem, that means the same geometry, by using a thin airfoil theory or potential flow or Euler equations instead of the Navier-Stokes equations. What would be the outcome if such theories were used? Can we at all use them? And if we use them, what outcomes are expected from them? So, let us try to raise these questions. So, there are other questions too. We need to recall the assumptions associated with each one of these models. That means, what were the assumptions we made when we discussed about thin airfoil theory, potential flow, Euler equation, etc. So, for example, in thin airfoil theory, you remember that we had talked about a vortex sheet, which we had distributed along the chord of the airfoil, and we said that the airfoil is so thin that even if it does have a camber, it kind of coincides with the chord line. That means, such a modeling already tells you that it works very well for only extremely thin airfoils, and even if you look at camber, the camber is virtually so small that it may as well be ignored. That kind of a situation is there. So, if you really make the airfoil much thicker or you add significant camber, that then will thin airfoil theory work? Probably not so satisfactorily. Then, if you recall about potential flow, we said that the first point where you started discussing about potential flow was that there can be no rotationality. So, the flow essentially has to be irrotational, and you know that all viscous flows would have rotationality anyway in the viscous dominated regions. That means, essentially you are trying to say that the flow has to be inviscid as well, and then we also imposed another condition for the kind of potential flow we discussed about, that is, we discussed it in the context of incompressible flow, but later on when we discussed about velocity potential equation, we extended it to rotational for compressible flows as well. What was the assumption for Euler equation? You remember that if you neglect the viscous terms in Navier-Stokes equations, then you will be able to get Euler equations. That means, Euler equations have all other features like Navier-Stokes equations, apart from only the viscous stress terms. So, keeping these assumptions very well in view, we need to understand what the capabilities of each one of these models would be, and from typical flow computations, results like the ones we can see over here, we should be able to backtrack that what could be the possible flow model which was used. So, the different approximations which are involved in the different flow models have to be very well set in your mind when you look at results like this. That is a very, very important message that we are trying to send. And then coming to the last bullet point, which aspects of the flow can be modeled and predicted well using the governing equations or a system of governing equations. So, that also should be well understood by you. For example, if prediction of CF is an important issue, then certainly thin airfoil theory, potential flow, Euler equation are not at all candidates which you should look at. You can start with the boundary layer equations if it does the job. If not, then you have to look at the Navier-Stokes equations. For using the boundary layer equations, you again have to be careful that the flow behaves like that, where the scale of the boundary layer thickness compared to the characteristic dimension of the flow is very, very small a number. Secondly, there can be no flow separation, which that theory can accommodate. So, if these are violated, then the only candidate left for you would be Navier-Stokes equations. So, this is where the practical applications of theories that you have learned are gradually becoming apparent, are gradually becoming clear to you. So, you have to in due course develop this intuition, develop this inclination, develop these abilities in order to use the tools of aerodynamics more and more rationally, more and more productively. Let us move on. We continue to have the same picture out here. It keeps us reminding that what problem we are trying to solve. We are trying to solve flow past an airfoil. So, we are still moving around that problem and we are trying to ask different kinds of questions. So, now we were talking about solving potential flow past the airfoil, and then you remember that the governing partial differential equation for the incompressible regime is Laplace equation, and there are certain elementary flows that we looked at which are solutions of Laplace equation. So, once you have the condition of irrotationality, you have the existence of a velocity potential phi, and you can then say that the phi distribution in the flow field can be obtained by solving Laplacian phi equal to 0 by applying suitable boundary conditions. And you need to know that if you are solving potential flow past an airfoil, what kind of boundary conditions are you going to apply? For example, you remember that this is an inviscid flow, therefore, the flow can slip on the body. So, the flow can have a tangential component on the surface, right. So, it can slip like this because you are discussing about inviscid flow, but it can never penetrate the surface. So, this is not at all allowed. Normal component of velocity has to be 0. So, this is precisely the boundary condition that you have to apply for any kind of inviscid flows that you are modeling. That is true for potential flow modeling as well as inviscid flow modeling using Euler equation, for example. Additionally, in potential flow, you have the presence of a velocity potential. So, what you end up solving is essentially phi at the end of the exercise. And then if you take the partial derivative of phi with respect to x and y, you end up getting the velocity components. While in Euler equation, for example, you solve for u's, v's directly, and you can even impose the Vn equal to 0 condition in terms of the velocities. Going back to the elementary flows that we learnt about as solutions of Laplace equation, we remember having come across uniform flow as one of the solutions. So, this was the first elementary flow that we learnt, and we see its application here when Navier-Stokes equation is being solved as well. Remember that it is not to be confused that uniform flow can occur only in potential flow. Uniform flow can occur in viscous flows as well. Only thing that we are saying is that in such a region there is no viscous shear. That means velocity gradients are absent. Gradients are absent, and therefore, what is the consequent? Tau will be absent, because tau x y is dependent on del u del y, del v del x and so on. So, here tau would be 0. So, it can exist in potential flow, it can as well exist in viscous flow. What about other elementary flows? We learned about source flow and sink flow. So, we learned about the stream function expressions or the phi for such flows, and then we learned about the point vortex flow or vortex flow, and for the first time we saw the presence of circulation. If we moved around a streamline around the point vortex, we found that there is a net non-zero circulation which is being produced by that point vortex. Again, we recall from the Kutta-Joukowski's theorem that the lift per unit span is given by the Kutta-Joukowski theorem, and it depends on the circulation around the concerned body. So, if you are approaching the problem of solving flow past an airfoil using these elementary flows or their combinations, can you have a numerical model to solve the problem which goes beyond the thin airfoil theory, for example. So, you do not want to live with the restrictions of the thin airfoil theory, you would like to solve for a thick airfoil and with significant camber, and if you really want to do that, thin airfoil theory may not give you very satisfactory answers, but a numerical model can, and that is what is called as a panel method. So, we will learn about that method as well in one of the upcoming lectures. It is a numerical tool or a model for solving two-dimensional potential flow past arbitrary geometries for that matter. So, it is not used for solving only airfoil flows, it can be used for other kinds of geometries also, but we have to again remember that the basic model does not have any potential to calculate drag forces. Only thing that it can predict is the Cp distribution on the body and the consequent Cl, and it is found that bodies which do not see much of flow separation, that means by and large the flow is attached to the body. In such cases, if you treat the flow to be largely inviscid in nature and you try to approximately solve the problem by considering it to be a potential flow, of course, by neglecting the fact that there would still be a boundary layer, there would still be viscous effects, rotationality, etc., but still try to solve for a potential flow past a geometry like that and try to compare what is the outcome in terms of the pressure distribution, you would get a reasonably good result, and that is where lies the strength of a model like this. So, that is briefly about the numerical technique which we call as panel method. Remember that in this method we do not solve for the entire flow field, but we try to solve for the pressure distribution on the body surface only by distributing elementary flows along the body surface. We do not distribute it along the chord line like we did for the thin airfoil theory. So, we had a vortex sheet disposed along the chord line in thin airfoil theory, but in the panel method we will not do that. If we have an airfoil like this, we will move around the actual geometry of the airfoil and we will distribute some elementary flows on these small elements which we will call as panels. So, you may like to distribute sources and sinks, you may like to distribute point vortices depending on what kind of flow you are modeling. So, if you are modeling a flow where circulation is 0, that means you are modeling a non-lifting flow, you can distribute point sources and sinks and combine it with an uniform flow to generate a non-lifting flow past an airfoil. Let us say a case like this: symmetric airfoil at 0 degree angle of attack. That kind of a flow would be categorized like that. But the difference is that here it is a Navier-Stokes solution, but this technique is based on solution of Laplace equation, and therefore, you would solve it as an inviscid one, and that too as a potential one. Okay. Whereas, if you are solving the problem as a lifting airfoil problem, then you have to bring in the concept of point vortices. So, in that case the panels will have to carry point vortices here. We will discuss more on this later, but we are gradually trying to introduce the ideas, the thoughts that we are having in our minds and trying to take it forward rationally. We come back to viscous dominated effects once again. We were discussing about potential flow for some time. Now, back to viscous effects again, and you can figure out that these are very much viscous flows where you can see large scale separation. Why is it? Because you are solving flow past an airfoil beyond stall. You can see instantaneous streamlines, you can see vorticity contours. So, they must be carrying information about the omega z component because it is a 2-dimensional flow. You can also see closer views of streamlines here, and you can see very large scale flow separation and large eddy or vortex structures. Interestingly, the flow has not separated on the windward side. So, on the windward side the flow is attached. The flow separation has occurred on the leeward side. Further, you might be observing that the stagnation point has moved away from the leading edge. I hope you can notice this, the location over here. So, it is slightly lower, which means it has moved away from the leading edge. We have learnt it in earlier classes that how to analyze these kind of flows on the leeward and windward surfaces. So, this sketch basically talks about the story on the windward surface where the flow essentially undergoes acceleration. That means favorable pressure gradient, and therefore, since the pressure, the static pressure is continuously dropping, the boundary layer remains robust, fed with enough momentum, and therefore, it does not separate. The opposite happens on the leeward side where the flow is getting decelerated, it is facing adverse pressure gradient, there is nothing to energize the flow, for the flow is moving uphill in terms of static pressure, and therefore, the obvious consequence is that it runs out of momentum. This is the point where shear stress reaches 0, that means it is on the verge of separation. We also say incipient separation, and then beyond that further downstream the flow has already separated. So, you have a reversed flow region. So, all that once again comes back to you when you look at the numerical results. So, here you can see large pockets of separated flow where it has even gone beyond an ordered structure like this, because very close to the leading edge itself the flow seems to have separated. So, it is like a leading edge separation which is in action currently. And as you can understand, in terms of integrated effect of pressure and skin friction, if you go ahead from your computational results, if you are able to integrate that, then you will come up with a very large drag. So, the CD would have gone up significantly, the CL would have fallen substantially, and therefore, your CL by CD ratio will be poor. So, it has become aerodynamically very inefficient at these angles. Again, remember that this is a viscous flow solution, that is why it is able to predict all these. It can predict flow separation, it can predict the post-stall behavior. If you were to use the thin airfoil theory, for example, what would be the consequence? Let us try to plot the CL alpha curve with thin airfoil theory. The thin airfoil theory predicts that the CL alpha curve goes on perpetually. The more you increase your alpha, the more the CL, but that never happens for a practical flow. So, the Navier-Stokes solution that you see over here predicts a stall, it droops down, and you are probably looking at the flow somewhere here or maybe here, where it has already stalled and you have moved into the post-stall region, and only Navier-Stokes equations can handle that, not even boundary layer equations will be able to handle it. So, we are negating most of the models in order to capture a physics of this kind. That means, thin airfoil theory, it cannot capture it, potential flow theory cannot capture it, because the flow is highly rotational. Euler equations cannot capture it, because it is a viscous dominated phenomenon. Boundary layer theory also cannot capture it, because you do not have an attached boundary layer here, you have a separated one. Therefore, all of these models fail and you are only left with Navier-Stokes equations. So, this is the process, the thought process that one has to go through before taking up a flow problem and trying to compute it. So, there is a lot of physics behind it, there is a lot of understanding of the theory behind all this, the physical phenomena, understanding of these phenomena, and only then can you get into the computations and then think about how to solve the set of partial differential equations which represent the flow field using your model of approximation. And once you are done with the solution, with the numbers that you generate, you again have to have the capability, the training, the experience to derive meaningful results out of it. So, we are trying to equip ourselves into a training of this process. Well, so we saw a single airfoil pitched up at a fairly large angle of attack and the flow has stalled. But well, does it mean that airfoils will never operate at fairly large angles of attack? Well, that is not true. So, if the airfoils have to operate at fairly large angles of attack under certain situations, what do we do? Do we encounter flow separation and accept the fact that they will be absolutely useless in terms of aerodynamic efficiency? Well, that will not serve the purpose, because in practical vehicles, if you come across such a crisis, the vehicle will probably lose altitude dramatically, it may even crash and things like that. So, what is the way out? We have discussed about it. The way out is to deploy high lift devices. We continue to discuss about the infinite section airfoil in either single element sense or, as we see over here, in multi element sense. We are yet to go into 3-dimensional bodies and discuss about computational results. But here for the first time we are looking at a computational result on a multi element configuration. So, this looks far more interesting of course also, and you can see colors, you can also see lines. So, these are often called as contour lines or iso contour lines. That means they represent equal values of the variable that you are plotting, so that if you follow each line, you know regions where the values are more or less equal. So, you go by the color as well as you also follow the lines, and then you have an enriched understanding of the regions essentially. So, you might notice here as well that colors are varying. So, you have a green region here by and large, a blue region here as well, and then there are some red regions and so on. So, I leave it to you to think later that what could be the variable that we are plotting over here. So, from your basic understanding, can you take a careful guess of what is being plotted? Well, without going into much of that, I am going to discuss more about what we learned earlier in terms of high lift devices and what further can we interpret from the picture that we have here, from the flow computation that we have here, right. So, here we see both leading and trailing edge high lift devices have been deployed. So, we have a slat here and we have a single element flap that has been deployed here, and interestingly what you see further is that there are regions which have gaps and there is flow moving through those gaps. So, you see a gap over here, you see another gap over here through which flow is moving from the windward side to the leeward side, and you may remember that we discussed about those kind of strategies being used in high lift devices. So, the intention behind using them is to create momentum injection to the leeward flow. And this flow that you are injecting with high momentum must nicely match with the leeward flow, so that the boundary layer gets energized. And what happens as a consequence is that the boundary layer, though it is going through a very stiff pressure gradient over here, it never separates. It nicely carries on against the adverse pressure gradient, because once again you have momentum injection over here, and that further keeps it energized to follow the multi element surfaces before it leaves smoothly from the trailing edge. So, that is the strategy. And from the flow features, we find that there is no large scale flow separation like effects that we can see over here. We do not see very large eddies, reverse flow or recirculating flow, etc., etc. So, that basically means that this is indeed generating substantially high lift. One more thing that you can figure out is that the flow perhaps is coming in at an angle over here. It is not a uniform flow which is really moving like this horizontally. That is another aspect that you have to notice. So, there is a lot that you can actually interpret from the pictorial representation of the flow. So, this is a kind of flow visualization also that we are doing. We are visualizing the flow by using the numerical data, using numerical data, you have other means of flow visualization also. If you are using practical or physical experiments in wind tunnels for example, there also you have means of visualizing the flow or picturizing the flow, and then it gets easier to understand some of the features which are not so easily understood when we discuss theory. So, this is where theory tries to give you the exposure, and then the computations are trying to build on them and augment them, giving you a deeper understanding. So, we recall about the application that during takeoff and landing phases of the aircraft, in order to increase the maximum lift coefficient, these high lift devices are deployed, and that ensures that the aircraft is still afloat at lower speeds close to the stall speed. So, this is typically the requirement during takeoff and landing. And as we remember that when we look at the trailing edge flaps, when they are deflected, then from a 0 flap deflection with a 10-degree single element flap deflection, there could be a delta CL of this order. We are of course looking at it qualitatively, but we are trying to understand once again that what happens in principle when you deflect the flap. And here we have cited the base airfoil as a symmetric airfoil. In multi-element configurations, of course, you can have a double slotted flap like what we have shown over here, we have discussed earlier. And in the case of leading edge flap or slats, essentially the CL alpha curve for the base airfoil gets a little further extended over here. It does not shift parallelly much, but it enhances the delta CL max. That is what comes from the leading edge flap in an activated position. Also remember that the moment you deploy these control surfaces, you are also enhancing the surface area, which means the net lift generating capability of the airfoil enhances further because of the effect of the area. It is not only the CL max effect, but it is also the area augmentation effect. Are all surfaces on an aircraft of a streamlined nature? The answer is no, unfortunately no, and that means there are surfaces which will increase the drag considerably. Sometimes it may be done with a purpose as well, but sometimes drag is a kind of a side effect which is produced when you deploy such a surface, but you do not have a choice. So, even there is a drag, you have to accept it. So, one such is the aircraft landing gear, for example. So, we are just seeing the landing gear part of the aircraft, we are not seeing the bottom portion of the aircraft from where the landing gear has been deployed. So, you can imagine that the main aircraft lies above, but we are concentrating on the flow around the landing gear only. And then what you see is over here they are vortex structures which have a lot of unsteady behavior, and they seem to be creating a lot of disturbances. In the wake of the landing gear. Once again, you cannot do it with inviscid models or potential flow models. So, it is again Navier-Stokes that you are solving over here. Additionally, you are seeing wave like structures over here. So, these could be pressure waves, maybe sound waves. these may be generating noise. We talked about acoustic effects at the trailing edge of airfoils and wings. So, acoustic effects may be coming from shapes and surfaces protruded into the flow like this, which are bluff in nature. So, remember here that we are talking about a bluff geometry essentially. It is certainly not a streamlined geometry. Okay. So, we had learned earlier about bluff body flows when we briefly looked at flow path cylinders. So, if you look at the cross section of the strut, for example, over here, this is a cylindrical section. The wheel portion is a little more complex in terms of geometry, but they are also bluff in nature. So, the concept of bluff body flows is going to be very useful in trying to understand these kind of flows past blunt surfaces. And then again you know that as Reynolds number varies, your nature of the wake would also vary. You could have a wider wake in the case of a subcritical flow, you would have a thinner wake in the case of supercritical flow. So, in this lecture once again we discussed more on certain flow features by recalling about the theoretical tools that we learned earlier and trying to fit them in as we look at computed results. And we looked at viscous flows primarily, but we also in between discussed about possible application of inviscid tools like the potential flow, Euler equations, etc. Thank you.